dig a little deeper into the operating system kernel. So there are a couple of terms that I've been using so far: kernel space and user space, right? So what I'm talking about here is a little bit of an informal definition, but hopefully it should be enough for you to get a reasonable understanding of what are the limitations and what exactly would classify as kernel space versus user space and so on. User space is typically any program that you directly run: a browser, an email client, a video player, right? All of those are the apps that you typically run. Each of those has limited privileges. Especially on a typical Windows laptop, you are probably the only user who's making use of it, or at least you think you are. The point is that there are a lot of different background processes that are running with different kinds of permissions. And technically, they are running as different users, right? But you don't really care because there's no other person actively using the system. On a server, on the other hand, right, whether it's a Windows server or a Linux server, typically multiple people are logged in at the same time. And if that happens, you need to make sure that the apps that each person runs have limited privileges. In particular, they should not be able to see data corresponding to another user, right? Or to modify something that someone else owns. And so how this happens is that even for something as simple as accessing a location in memory, or perhaps for reading something from disk, you cannot directly go and activate the registers corresponding to that peripheral and try to pull data out of it. Let's say we are talking about a PWM timer module. I cannot allow some arbitrary user to just go in there and directly start poking at address 4000, whatever that number was, right? Instead, they have to make a request to the operating system, and that is done using something called a system call or a syscall. So syscalls are a very crucial part of how operating systems work, right? Pretty much everything where the user space needs to interact with something that is managed by the OS is handled through syscalls. Now, on the other hand, syscalls themselves need to be handled, meaning that they actually have to do some work. That is done in kernel space, right? This is basically the core operating system and the device drivers, and they have full access to the system, to the hardware connected with the computing system, which means that the core OS can go and read any file technically, right? Can activate or deactivate any of the network interfaces, can access any part of memory that's available in the system. But of course, it's not a process by itself. It's just that it has the capability of accessing all of these things. Its job, the kernel's job, is to basically provide suitable interfaces through syscalls by which other programs can actually make use of all these resources. Now, the boundary between kernel space and user space is usually done in the context of Linux heavily by means of using something called files. So Linux uses the interface where every device it tries to make it look like a file, right? Even if technically speaking, it doesn't normally behave like a file. We'll see later that, even the timer, we will sort of make it look like a file, because then we can use some standard functions that are already available to us in order to actually communicate with the device without having to write fresh new functions depending on the kind of functionality that the device requires. In particular, there is something called the IO control command, which we will talk about briefly later. There is mmap, which in this case can be used to map a region of memory into another set of addresses for access. What we will be looking at is another variant of a related function, which is called IO remap. But more importantly, it also provides interfaces called sysfs, right? Which, if you're on a Linux system, you might have seen that there is a set of files under the hierarchy /sys, right? So these are essentially what are called the system files. And this is actually a virtual file system. Those files are not real files, right? They only look like files because the operating system presents them to you like files. They do not exist somewhere on the disk. There are no sort of bytes stored on the disk corresponding to any of the files present over there. When the operating system starts up, it creates a virtual file system and pretends that you can access these just like regular files that are present on disk. a very useful abstraction, which sort of makes it easy to view various parts of the operating system in a convenient way for users. So the design goal of all of this is to provide safe and simple interfaces for the users. And files are probably a very simple and clean abstraction, which can be built around very nicely. So how does all of this work? How do I, in particular, manage to keep this difference between the kernel space and user space? This is done using something called privilege levels in a CPU, right? And what happens with a privilege level is that the CPU itself, the actual hardware of the CPU, has special instructions which allow it to change what's called the privilege level. And these are essentially referred to as different rings, right? So commonly, what we call as ring 0 is what's called the most privileged mode. It's usually what is used for kernel mode, right? So what happens in ring 0 is it pretty much has access to everything that the CPU can do. There is another mode which could be ring 3, it could be something else. This depends on the CPU that you are dealing with, right? Which has less privileges, right? It's sort of, when you look at a picture like this, it can be a little confusing because it gives the impression that user mode is a superset of kernel mode. That's not what this is trying to convey. This is trying to convey that the innermost ring is the most powerful one, the one that can do pretty much anything. The user mode can get access to the inner mode primarily through means of system calls. Okay, so system calls allow us to invoke privileged operations, which can only be done by the kernel, right? By essentially having some kind of a function call, which will come in here. The kernel does something and then returns a value back to us. Another way by which I can switch from user mode to kernel mode is when an interrupt occurs. It could be as simple as, a key being pressed on a keyboard. At the end of the day, what that actually does is that when you press that key, that generates an interrupt. It stops the user mode program, switches into kernel mode, handles the key press by putting the byte somewhere in memory, returns back. All of this happens so fast that you don't even notice that anything has changed, right? So these different rings of operation are part of the CPU construction. You need a CPU that provides the capabilities of having these different rings of privileges, right? And if you do, then you can basically build an operating system that has this kind of privilege separation. Now, what do we mean by privileged operations? Pretty much anything which requires directly accessing the registers for a device, configuring interrupts, controlling things like direct memory access or the memory management units, managing page tables. Page table is something that I'm just going to mention and move on. This relates to how memory is managed. It's a fairly complicated topic, but very important from the point of view of how memory is managed in a system. And of course, also power management, right? For example, you're probably used to the fact that when you just close the lid of your laptop, it goes into a sleep mode, right? Now, how does it do that? It basically, the CPU tells all the peripherals to sort of suspend themselves, go into a mode where they can recover from it, but are currently not doing anything. And then it basically sort of puts all devices into a ultra low power mode, right? So all of this power management, it can't be that any user process can just trigger that off. At the same time, it shouldn't be that in order to run this, I need to have some special access to the system. So what is done is the user mode program will call a function, which is a system call, which in turn will take the system into kernel mode. The kernel mode will check whether, the privileges are okay, whether this function is permitted to be called right now. And if it is, yes, it will do whatever is required. And the request is accomplished. Okay. So user mode cannot perform any of these tasks directly. It has to call into the kernel, which will do the job and give it back. Something as simple as a printf technically involves system calls. Why? Because printf involves putting something onto the screen of your system, which means interacting with the device, which means that at some level, somewhere along the way, I need to go into privileged mode so that I can actually send the data into the device driver and thereby into the device so that it can actually get displayed on the screen. So to summarize, kernel space versus user space, user mode cannot execute any privileged operations, right? It transitions into the kernel via system calls or interrupts or faults, which could be something like maybe it tries to access a location in memory that is not supposed to be accessed. That will trigger an exception or a fault, which in turn is handled by the operating system. It could be other kinds of faults that happen, either hardware-based faults or typically many software-based faults are also present. Now, drivers need to run in kernel mode because they have to touch the hardware. They actually have to send data to the hardware or get data from the hardware. And in order to do that, you need to be in privileged mode or kernel mode.